Hello, I'm Jesús Labarta, and I'm going to give a brief introduction to Paraver, the performance analysis tool developed at BSC for looking at the performance of parallel programs. My main objective is to describe the features and essentially the philosophy on how to use it. It will be an introductory description, which will start by presenting a little bit the framework and the tools and the tool itself. And we'll provide also some additional information for later study if you are interested in, but I will focus important part of the presentation in a real life demo to exemplify the concepts. Let me start by mentioning the BSC2 framework, which consists of different modules and starts by the extract instrumentation package, which essentially captures during the application execution the events that characterize, that describe its behavior, and stores them in a trace file. Well, in reality, we generate extract generates 3 files. The main one is peer.prv, which is has the numerical value, the timestamped events, but there are additional files with some additional symbolic information. These trace files are visualized by Paraver. This is going to be the main focus of today's presentation, is the browser which looks at them. Although the whole environment has additional paths. For example, a path like this will let you do what-if analysis and study possible additional behaviors of the application. There are paths like this one where we will be doing actually analytics on the performance data of the trace data, including clustering techniques and doing tracking and models. So it's a wide and a powerful framework. But today's objective is to look at the browser, the visualizer itself. And I will start by briefly introducing the format of the trace. The trace essentially is an ASCII file, which has lines. Each of those lines has a timestamp, which is time in nanoseconds. And has, after that, a sequence of events, each event described by 2 numbers. The first is what we call the type of the event, and can encode, for example, things like these are user functions or these are MPI calls, or can also encode things like these are hardware counters. And the value that in the 2 first previous cases that I mentioned would be the identifier of the function being entered, and in the last case would be the actual value of the actual hardware count. This is the main structure. Just to mention a little bit also that also each line contains an identification of the object of the thread that incur or perform those activities, those events, and it's encoded by 3 numbers saying of which application we are doing. Each application can be MPI, so the second number is the rank, the MPI process, the number of MPI process, and the third number is the number of thread within the MPI process. This is the trace that is captured by extract, or you could generate with other instrumentation packages. And what Paraver does is just browsing it. These additional files, which include symbolic information, essentially translate from those type numbers that we saw to actually a string that is more human readable, or from values. We say, for example, this event is the MPI point-to-point calls event, and value 4 represents, for example, MPI I receives. So this is symbolic information. So in this context, what is Paraver? It's just a browser, okay? It just lets you visualize, yes, but it also lets you manipulate, filter, or cut traces. Today we will focus on the visualization aspect. And it's a browser for traces, so sequences of timestamped events. One important characteristic is agnostic of the trace encoding semantics. In whatever those types mean for is really not something that Paraver deals with. Paraver only deals with a mathematical method to convert those sequences of timestamp events into functions of time, and to operate with those functions of time, and to get apply statistics on those functions of time. In this way, the tool, which we essentially use for performance analysis, is a tool that can be used for other things, and we have used it, I don't know, for analysis of the behavior of tooling machinery in heavyweight industry, for example. I will also mention a little bit about this multispectral philosophy, about how we think the tool should be best used. But let me start by the mathematical foundation, which is, in reality, this is kind of Paraver in one slide, okay? And essentially what we display is timelines. So time in this dimension and one row per thread. And what the very important thing is, what we display are functions of time. We display piecewise constant functions of time. So in a given interval, they have a given value. Next interval, maybe the same or maybe a different value. So it's a function, piecewise constant function of time. We use as the semantic. This is what semantic that encodes what this number represents. This number can be the identifier of the MPI column in, or can be the number of cache misses I've done, or can be the instructions per cycle that I've done in this interval. These intervals are not uniformly distributed. Actually, they depend from the activity of the program when it enters and exits runtimes to the runtime system typically. So some of them may be very short, some of them may be significantly larger. So what we have is many of these functions of time for each window, so one per thread. And what we have to do is to display those many functions of time, and we have to render them. In the case this semantic value is a categorical value, is a limited number of values, possible values, we can translate it by a color table. In the case it is a real valued function, we translate it through a gradient. We represent it as a gradient that typically in our case goes from light green to dark blue. We also have, in the case of typically the value of 0 typically is represented as the background color. So this is the display. One of the important things of this display is that it is we use non-linear rendering capabilities. There's in a pixel there may be a lot of threads and a lot of time intervals that might want to put a value. So we have to apply some way of deciding which value is being put. So these are timelines. We also have associated to timelines, we can build tables, and in the table you get rid of the time dimension, and you get in the table also one row per thread, yes, but only one column per possible value in this function of time. If the function of time was categorical, this table would actually contain typically what we understand as profiles. In every entry you have a given statistic whenever you were in a given, for example, in a given MPI call. In the case of real valued functions or with a large dynamic range in the value, what you will end up having is histograms. You will have of course not one column for every value, but one column for every bin, every range of values, and you have histograms. What we have is a very flexible also mechanism from going from timelines to tables and from tables to timelines. Those are the only two display mechanisms that we have in Paraver. You can, if you want to present other kind of plots, you can save the data in ASCII format, and you can use, I don't know, Excel or whatever to do further analysis of the numerical values. The important thing also here is how do we build the function of time? And the function of time, which is then displayed, is actually obtained from the original trace by filtering the type of events that we may be interested in for a given view. If this is MPI calls, we are only interested here on the MPI call events, and then applying what is kind of the heart of the engine of the tool, which is the semantic module, which transforms that function of time into that sequence of events into a function of time. So this semantic module generates the different semantic values and the points in time where they start the value. And this is an extremely flexible mechanism, and this is what gives the big power to the tool. The setup of this filter, semantic, and display can be done graphically, but it may be a little bit long, a little bit cumbersome. So what do we do to make things easier? We can save that setup into what we call configuration files. And later, one can just load those configuration files, and the views exposing the desired metrics appear directly. These configuration files can be used also for checkpointing of your analysis. They can be used for cooperative analysis between different people, or they can even be used for reporting bugs to us when you may think I should be seeing that and I don't see it. That's the right way of reporting bugs to us. So these configuration files are distributed. Some of those come with the distribution. Some of those you can make your own. Let me go back to this other point, which I think was very, very important, which is this multispectral imaging. It's something that you use in many other areas of science, where you actually look at one reality with different spectral bands or with different filters, let's say, or light sources, because each of those has kind of some particular characteristic inside that they provide, okay? And we leverage the high capability of the human mind to correlate those things, or we can even derive combined metrics that correlate those things, and that's a way to get in kind of broad information on the behavior of systems that can be, for example, very, very large. So what does that mean in our case? In our case, it means that we like to have these timelines, for example, for the same region of time, for the same number of threads, but each of those representing a different metric. Here I have a small example. This is MPI calls. Here at the bottom, this is actually the identifier of the routine that calls MPI. And these are other ones that are representing metrics like IPC, instructions per cycle, or like misses per 1,000 instructions, or like duration of the computation. Each of those things, by looking at different of these views, you can actually start thinking or speculating or behaviors that may appear, and you can start saying, oh yeah, this performance, this IPC is good here because these cache misses there are bad or good, or one can make their own speculations. That's the capabilities of the tool. This can happen also at the level of MPI profiles, you can represent or function profiles, whatever you can represent on tables different metrics, which actually show a little bit this multispectral view at one reality. There's showing some of these possible statistics or metrics. Also with histograms, I am not going to look at this on the slides. I prefer to look at these things on the demo. So before finalizing the presentation, I will just insist that essentially this is nothing but a tool, nothing but an instrument. It's like a telescope. It's something that lets you look at the reality, lets you generate hypotheses, and lets you obtain the evidences that can verify or reject those hypotheses. If you have the data, given enough data in your trace to verify those hypotheses, the tool should be able to squeeze that data and obtain it, either by using the configuration files that we provide or by developing your own configuration files in case of very advanced kind of needs. We do provide, as I said, configuration files to display many metrics that may be of relevant interest. And it's a little bit a methodological aspect, and this I think is what is important, is that you have to know what to look for. You have to decide which of these things is the thing that can help you validate your hypothesis and use that specific metric for that analysis. Just as a little bit of additional material, if you want to look at it, first you have in the BSC tools, you can download the tools, and you can download also tutorials and kind of guided training material integrated into the tool itself for the navigational aspects. But what I think is very important and is that you should be using the tools with a high level global vision of what to look for. And so the methodological aspects are very, very important, and this is the kind of things that we have tried to push and promote within the Prof project. We have already done several webinars explaining some of these methodological aspects. You have a further online training material also in the web page of the project. So having done this very general presentation, I would like to switch to the online demonstration. So let me do the switch now. Let me select the Windows, sorry, a virtual machine where I have Paraver already loaded a trace. I actually said Paraver load the trace. The trace is already loaded. What I'm showing here is some configuration files that I have prepared. And essentially, I will start by applying to the loaded trace a given configuration file, which actually, following this multispectral methodology, is going to show 3 views, and that represent the whole trace file. The one on top is the MPI calls, and you, by moving the mouse on top of it, you see whether you are in MPI, which MPI call. You can double click and you will see the table of colors. In this case, you see the translation table that says every color what it represents. We have other views that are represented by gradients, and this is MIPS, instructions million instructions per second. And in this one, the coloring scheme is a gradient between light green, meaning low, very low MIPS, to dark blue, meaning high MIPS. In reality, there is here that you have the limits, what is considered low, what is considered high in this coloring, in this gradient coloring. You can change it. The important thing is also that here we also have a non-linear kind of stuff. Besides having very few levels of colors, everything that goes above this number here, which is this number here, everything would appear as orange, and everything below this other one will appear as light orange. So this is the coloring characteristics. The windows, you can navigate on them, and actually I can zoom in one of them, and one of the things I've done here is I have synchronized them. So I have declared the group of synchronized windows, and whenever zooming in one, the 3 of them belong to the group. Whenever zooming in one of those, I will be zooming in the other. Whenever fitting right bottom, fitting the time scale in one of those, I'll be fitting the time scale in the other. I can also clone a window, and let me take it out of the group. Maybe I can even create a new group, and this now should be visible. This should be belonging to group 2. What I wanted to show on this one of MIPS is, for example, that I can also zoom select a certain set of processes. Control and selecting an area will select the set of processes, and I can focus on, let's say, 2 of those. For example, I can. So this is an additional navigation where I can zoom into a selected set of processes. I can do the same thing on this other window. I can maybe shift it to the other group. It now has the same time interval as the one on top, more threads, all the threads, so I can actually copy and paste the objects. And I have the 2 windows at the same time scale, and with the 2 and representing the same actually the same objects. Okay. So we said these things are functions of time. So let me actually fit the time scale. They are functions of time. We have on the right button here the paint as is what decides how are we displaying this, and we can paint it as functions of time. And you see the semantics of or the aspect of a function of time. Of course, for 2, this might be fine. This might be okay. For 100 or for 1,000 or for 10,000, this kind of display is not as informative as the gradient coloring that we have. The other thing is everything we said, every window are functions of time. So if this is a function of time that has a dynamic range, which is in this range, this one is also a function of time, and we can paint it as a function line, and it is a function of time. Well, it's with the range that I have here, we see very little variability. We can do a fit the semantic scale of both, and this is fitting the range. And what we see is that here we have a function of time that takes values between 3 and 10. So these are the identifiers of the different MPI calls. This being MPI calls is much more informative for this view to paint as a column, translating by a color code table. So, but this is very, very important. Always keep in mind that you have functions of time that can have a lot of variability inside. So a lot of variability till you get to the innermost levels. The next thing that I would like to highlight or express, devote a little bit more of time is to the rendering aspects. And I'm going to get rid of these views, and I'm going to, you have seen that we can have many in time intervals, many of these bursts, these time intervals we call bursts. Many of them may be trying to paint something into the screen. Sometimes people is tempted to increase the size of the window, okay? This is something that you can do only up to a certain limit and will reduce your multi-scale capability of analysis and will not allow you to escape from a fundamental problem, which is how to convey such a large amount of information through a screen to a human mind. And very often the limit is in your eye far more than on the number of pixels available on the screen. So what we have to do is we have to address this or leverage the capability of this need of rendering to actually convey information, the maximum possible information from the internal engine of the tool to the human brain. And rendering is one of these functions, is one of the approaches. The rendering is specified here, and in this case, for this MPI call view, the render that was set up, you see there are many options, but this one, random not zero, means that the renderer will put a value of one of the values that somebody of the threads or of the time intervals tries to put into a given pixel, as long as this value is not zero, and we'll select one of them at random. And you may think this is a very nonlinear thing, very variable, but it actually gives information about the structure of the application, about the variability. You can see those things. You could render with other mechanisms. For example, you could render with the maximum. So the maximum value of the function of time for every that fits into a pixel will be displayed. And in this case, for example, it's MPI weight all because it happens that MPI weight all has the highest identifier. My message or my point is that one has to be always aware of this rendering characteristic, this fact that you always have to do this kind of rendering. Take care not to be misled by some of these things, and maybe of course you can always drill down and zoom, but you can play actually with different renderings. Like as we said, you can play with a purely random rendering, okay? And you can play with for this case, probably the most useful probably is this random not zero for MPI calls. The same rendering things, the same rendering mechanisms apply to these other functions of time that have, for example, a real valued semantic. You can apply with, in this case, if you look at it, I had it with a maximum. I can draw with a random not zero, for example. By the way, things change a lot between the maximum and a random not zero. The question is, does a random not zero is the most appropriate for this metric? And in metrics that are real valued performance indices, let's say, maybe there is one other rendering, and in this case, a linear one, which would be just the average, for example, or the average of values that are not zero. And this may be semantically relevant. We try to provide the configuration file that we provide with possible relevant renderings, but in all cases, be aware of that and consider that in reality, the thing is you are really looking at a huge amount of data on a small window. And as I said before, doing the small bigger will very seldom be sufficiently large to represent the huge amounts of data that we try to look at, and your eye will often be the limit. So this was about timelines and rendering. What I wanted to shift now is onto looking at histograms. We said that from every timeline, we can build a histogram. We do it by clicking on this button here, this new histogram, third button, and it's selecting the timeline, and you have the histogram. Let me paint the colors, and you see that for every color here, we have one column. Well, essentially, some of those have no values in it. So essentially, this means that for the column for MPI broadcast, which has a numerical encoding, which is after MPI weight all, there is no actual value. In the cells, we'll have statistics that can be time or can be many other statistics I will show in a minute. But the important thing is we have one column per possible value of this timeline. Let me go into look at the actual values that we have. And for example, the statistics that we can put can be kind of controlled with this thing. And for example, we have now time. It means that thread 3 spent 13.29 milliseconds inside MPI sent throughout the whole execution. I can change the statistic to represent number of bursts, number of intervals, these intervals of piecewise constant, and it's 544. So there were 545 instances of MPI sent with had the total time that we saw before, but for which we can represent the average duration, for example, of each of these calls, or we can even do other statistics, like, for example, we can actually do the integral. And the integral also always has to be the integral of something, of some function. And this other function is, you can program it, you can choose it, and you can choose any of the other windows as the one you are integrated, and probably this one makes sense, integrating MIPS. If MIPS is instructions per second, what is the integral of that? The integral of that is instructions. What we show is that the tool can tell you, for example, by doing this computation, you can tell the total number of instructions that are being executed within MPI send throughout the whole execution. Whether this is a very important metric or is something that you would only look very late in your analysis, I'm trying just to show the capabilities of the tool. And one has to really be driven by a methodology, by a certain good vision of what to look for. But the idea is that the tool has the ability to do very detailed statistics. And what is important is that in the same way that timelines are kind of subjective representations of the whole data, tables are numerically precise, numerically accurate. And if they tell you this is the number of instructions, that's the number of instructions. You cannot really see the number of MPI calls from this thing, but you can really see the number of MPI calls, from here. And by the way, we see something strange, which is there are MPI receives here, but do we see them in the timeline? So can we see them in the timeline? And the thing is, we have this mechanism to go from tables back to timelines, selecting some columns, and then showing a timeline that only takes the value in those places where the original root function has that value. And it only does that for the threads where this happens. So I can copy and paste the objects for that, for example. And I really see that it's only on the last processes that I do the MPI receives, but not only in this intensive communication part, but actually it happens all over through all the communication phases. So this mechanism of going from timelines from tables to timelines is also a very powerful mechanism to find needles in haystacks. As I said, the tables can be computed for every view. So every view is functions of time, and every view, every timeline can be, from it we can derive a histogram of tables. So let's click on this one, let's click again, I want to do a table of that, and I will get a histogram of the useful duration. How long are the different computations? So here, let me just show you that in the control window is what determines what are the bins, and I'm going to make it in bins of going from 0 to this number. Let me get rid of the decimals, and let me go in increments of 500, for example. I'm here setting the bins of the histogram. I can allow it to redraw instead of doing redraw every instance. And I can really see the same thing that I had before. Between 0 and 500 microseconds, I've spent this much time. I can change the statistic. Where do I have the statistic? Is here. I can change the statistic, and it can be the number of times, the number of instances. So I have spent, in thread 4 has spent 13 times in total with a computation which had between 500 and microseconds and one millisecond. This is a histogram thus. The statistic, let me put the statistic back to be time, for example. Ideally, one would like to have vertical lines, which represents that every thread typically has some computation of the same, all of them of the same duration. Here we have this kind of patterns that indicate some level of imbalance. The mechanism for going from tables to timelines is always valid. So I can click here, I can select the range of values, and I will see where in the timeline that was happening. And this is happening here. And if I fit the semantic scale of this, I will see that I have longer executions here, shorter executions there, as displayed by this histogram. If I zoom in a region here, I have that synchronized. I could actually copy and paste the time and do the analysis only on that part of the timeline. Okay, so you have these two views, and with them you can navigate from one to the other, and vice versa. This was kind of the basics of the navigation. So let me do just one very small thing to finalize, which is just to show you a little bit some other configuration files that one can load. I have, for example, several metrics on the scalar performance of the code. By the way, it tells me that some of the things that I want to display are not, there is no information in the trace, so it won't be able to display that metric. But we have here in metrics which show how long is the duration of the computation, how many MIPS, what's the IPC instructions per cycle, very good here, very bad here. What is the L1 cache misses per 1,000 instructions? Nothing about L2 cache misses, so this event was not in the trace, and you'll have to look at the extract to determine which events you have captured, and L3 cache misses per 1,000 instructions. I have other views, for example, having to do with MPI metrics, and we have seen some of those, some metrics, but so we have seen the MPI calls, but we can display the message size. Or we can, if we know the message size and the duration of the call, we can display the bandwidth, the megabytes per second, the effective megabyte per second. Or we can also, I didn't talk about this, but you can also aggregate in the vertical dimension and show a single aggregated metric for the whole thing, and you have the overall aggregated metric for the whole execution. In this case, what is the instantaneous aggregated bandwidth in the system? So you have a huge flexibility, and as we said before, every timeline you can build an histogram. This timeline is message sizes. So you have here a histogram of message sizes, and we see that sometimes the messages are larger, sometimes they are shorter, and sometimes shorter. You can actually display this information and browse it and look for certain, I don't know, there's a final thing, let me just to close, is that you can, in this table, you can actually do a kind of third dimension, which actually shows you, instead of the overall message size, the histogram of message sizes overall, you can actually add an additional dimension where you see a plane for every MPI call. So you have a plane for MPI received. These are the message sizes for the MPI received, message sizes for the iSends, message sizes for the wait alls, message sizes for the all reduces. So I think this is given a fast overview of the tool itself, the capabilities of analysis. As I said, you have further material to get familiar with it. What I would certainly insist is that it is important to first apply these methodological aspects and to really have a guidance on what to look at and in which order. Otherwise, it's easy to get trapped into a kind of black hole, a local minima, where you try to look at things, but you sometimes lose this vision of the whole, so the forest, rather than looking at a few trees and not seeing the whole forest. With this, I finish the presentation and demonstration, and I'm open to questions. I understand you can put the questions, and I've seen a couple of them. One of them is Paraver used to trace GPU also or hybrid applications? And the answer is yes for MPI and MPI plus OpenMP. As we said, it's certainly supported in the trace. There's space for putting that information, and Extrai does support it. For GPUs, Extrai also supports it. So we can really do the three things: MPI plus OpenMP, MPI plus GPUs. There's another question is about my parallel code uses forked processes and 0NQ for communication. Can I use Paraver? Extrai itself does not instrument 0NQ, for example. We did have features for instrumenting forking processes. There's probably, if you have a lot of interest, we can really talk about that with our development people. We have had some at some point in time, certainly not for 0MQ, but we have mechanisms to instrument user functions, and the API, for example, can be intercepted that way. But in general, I mean, there is other people, for example, which has done translators from strace to Paraver, okay, so that you can visualize strace activity. So it's a little bit up to that. In some areas, people has done their own instrumentations, and the browser is a generic thing that is valid for this MPI plus OpenMP Pro or plus GPU, but also could be used for processes and 0NQ. We use it for other environments like PyCons, where we have actually different processes. Yes. Can you map a trace back to the source code? I showed some of the views, and I didn't show this one right now. Sorry, it's not this configure. This thing is, I had another view here, which is multispectral links to source. So I can load this, and this is popping up. Oh, by the way, maybe I've missed. Yeah, there is some events. That window shows many other things. Probably that configuration shows many other things, but the ones I wanted to show is, it actually shows a table. The single configuration file loads both table and timelines, of course, and it shows a table. This one is a profile of MPI caller, so it tells you, and same thing as the statistic, how much time you spent in MPI when it was called from inside this routine, or from, you see the routine here at the bottom, the name of. So when was it called from this routine, and it tells you the time. These are the number of at the level of routine. And of course, from every timeline, you can go also to the control window. Is from every profile, from every table, you can go to the control window. Here you have from which routine is actually the MPI call being done. So this is a view at the level of MPI callers. You can actually have 4 different levels of the call stack. And this is in terms of caller lines. You can also have in terms of line, source code line, where was this MPI call made? And you have the profiles, and as, for example, you can say, you can change always the statistics as we saw, and you can say where is this routine, the MPI call from this source code line, and this is all the places where the MPI is called from that source line. Of course, the default instrumentation packages of Paraver instrument only entry and exit of MPI and OpenMP, of the runtime calls, which means that in the regions that have no MPI, are just plain scalar code, there is no instrumentation, not captured data. That's the default instrumentation of Stray. We have a sampling mechanisms where we periodically get sampled information like any other statistical sampling-based profile. And then in those cases, you do display the same timelines with information also not only for the entries and exit of MPI, but also for the useful computations. How long do you think it would take to an average physicist to get used to Paraver? I mean, I'm not claiming that this is a very trivial thing. It's something that you can do in a day. Sometimes understanding what is a function of time, it's kind of curious, but understanding this idea of functions of time, understanding this idea of rendering, is something that actually takes significant amount of time and to mature. And what it all depends on whether you appreciate or not appreciate the effort and the information that you can extract. Okay, in POP, sometimes what essentially we end up doing is we do the analysis ourselves, and we end up showing the timelines to people. And very often, and it's true that it's not always, very often we have requests from the people to say, well, I would like to do it myself, and then we point them to this training material. But it's true that it's like any other. If you take any other GUI from any other tool, it's a little bit particular or special. The important thing, and this was the message I would like to highlight. The important thing is understanding this idea of functions of time and of rendering. Among the many CSV files, which are the most important ones? So this is where I point you to the other webinars looking at methodology. I think that's the most important thing, and in POP we are trying to push that, and the methodology we kind of point to something which tells you fundamental concepts of parallelism that appear, on how much they appear, and how much relevant they are in your behavior of your application. And if the thing tells you, if the model tells you that your problem is a load balance problem, please don't go and look at the MPI. Don't look at MPI profiles. Look at computation and useful computations, which means looking at useful duration timelines, looking at histograms of distribution. So in these presentations and this tutorial about the methodology, we try to explain a little bit this kind of hierarchical top-down approach that I think is what really is the most important way of approaching analysis of an application. Yes. Is there an option to analyze MPI programs without MPI? Of course, yes. See, yeah, that's certainly possible. Okay, we have also pthreads if you want. That's certainly possible. More. Let me see if I see more questions. What impact on runtime of time and data does using Paraver incur? What impact you mean overheads? So the overheads. So Paraver itself on the code is a post-mortem browser, so it's nothing on runtime. So it's extra is the instrumentation package which captures the information, and then you have to be also aware, certainly it does have a little bit of overhead. I always insist that it's always better to have information without overhead and being able to browse it and navigate it than, because of some overhead, discarding the information. I use the example of people looking at I don't know, Neanderthals, and if you look at Neanderthal, the guys looking at that, they use very, very, very corrupted data, and they tell us a lot of things that are probably very, very highly close to what was the reality. So I like to use that example. It does have overhead, yes, a little bit of overhead. You have to be aware of that, and it's little bit of overhead is what is the overhead of one probe compared to the overhead of an MPI. Maybe you want to blame half and half. So in the regions that have very, very, very extremely fine-grained MPI sequences of MPI calls, you can blame Paraver extrae, not Paraver. You can blame extrae half of the time and MPI half of the time. But the problem, if you are in that situation, you do have a problem independent of whether Paraver or extrae. You have a problem of extremely fine granularity, and your code will not scale. If you double the number of processors, you are in the same situation. So of having too much overhead without instrumentation. If you double the number of processors without instrumentation, you are in that situation. So my message would be, it's very, very important to be able to get insight and to get information, being aware that that can be, in some cases, in very, very fine grains, can be some overhead, but I think it's still extremely useful. Some information is much better than no information. You have had Paraver crash for very large traces. Yes. My message is Well, I don't know how you consider, how you measure patience, in what units. You measure patience in seconds, in kilograms, or in, I measure patience in megabytes, okay? And I measure patience in the amount of megabytes that I'm able to stand and navigate with Paraver in a trace. And to me, this is in the order of my patience is in the order of 200 or 300, 400, up to 500 megabytes. What if your traces are larger? We do have mechanisms for reducing the trace file, for looking at the relevant periods. I mean, it's like if you go to Siberia and you find a mammoth in the permafrost and you want to sequence it. Okay, yeah, you don't put the whole mammoth in the sequencer. You obtain a sample and you analyze the sample. So we have a lot of methodology for that. And I think in the POP website, there is also information of how to handle it, and certainly true. If your traces get above 500 megabytes, you should start using those mechanisms, yes. Is it possible to annotate particular times during program execution by text so that there is display in the graphs? You can, yes, you can. You have an API if you have the source code, because sometimes we do analysis without the source code, only with binaries. But if you have the source code, you can link with an API, which lets you emit additional events. And in those events, you can emit your additional, I don't know, you may want to see what is the evolution of the value of one variable. Every time you change it, you can, or every iteration, let's say, you can emit that variable into the trace file, and you will see a function of time that will be how that variable evolves along time. I guess this is the kind of question that you had. Yes, you can, and I think it's very powerful. And in reality, you can put any variable. So you can put variables having to do with the algorithmics of the program rather than with what we capture with the MPI call, which is only about the program structure aspects. Is it possible to use Paraver to verify the overlap between communication and computation and communication in MPI? Yes. You can, and I didn't show here, but some of I showed the metrics about bandwidth, for example. We have a whole bunch of metrics about bandwidth, and you can measure the actual bandwidth observed, the actual duration of the MPI calls, correlating these things with the message sizes that you can also visualize. You can really get a fairly good understanding to what extent was the actual overlap of data and computation happen or not. Very often people believe that by just using MPI, I send and I received, I'm done, I got my overlap between communication and computation. Very seldom the case, okay? So it's good to analyze it, and yes, you can analyze that with Paraver. So I think that by now we are gone through we have gone over the allocated period. I apologize. Hope it was interesting and useful, and certainly if you have some additional questions, please don't hesitate to address it to me. Thank you very much. Bye.